Okay, what slide? Okay, here we go. All right. Hi. I was still waiting for a few people to come in. I'm Brett Slatkin. I'm a software engineer on the Google App Engine team. Hope I'm in the right room. Is that what you guys are here for? Hopefully. Yeah, this is awesome. So many people showed up. So today I'm going to be talking about building scalable web applications with Google App Engine. And this is a very broad topic, so I'm not going to be able to cover everything in an hour, but I'm going to kind of go over what I think some useful takeaways when you're building App Engine applications. So here's the agenda. We're going to talk about using Python, the Python runtime effectively. Then we're going to talk about numbers that everyone should know. We'll get into what that means. We'll talk about the tools that we give you for storing and scaling large data sets with App Engine. And then I'll go through a couple of examples of kind of difficult things to do with App Engine that you can make easier by kind of following some guidelines. All right, so a lot of these kind of general ideas translate to any web application system, infrastructure, platform, whatever you want to call it. So to start off, prevent repeated wasteful work. Don't do it twice if you could just do it once. That's a very simple thing to say, but when you're trying to hack out an application really quickly, a lot of people forget that, and it actually, especially in the case of scaling to millions of users and hundreds of queries per second, it's really important. So in App Engine, this means a lot of things. For starters, it means using Python effectively. So in Python, you have a series of modules that kind of make up your application, what your application consists of. And when a request comes in, we load those up for you, and then we dispatch the request to them. Well, loading modules can be slow. It's not instantaneous. We need to get them loaded into the interpreter and start executing them. And kind of one of the simplest things you can do, just write out basically in any application, is you can define a main function. So this is really simple. It's in the documentation right now under app caching. It's a section in the docs. But if you define that main function, we actually look for that. So anytime we dispatch a request handler to a file you've specified, we'll check to see if there's a main function there, and we'll just reuse it. And so in that case, that means every request that comes in, we don't actually have to load any of the Python code. So we can very quickly execute. Another thing, these are just kind of Python idioms. Lazy loading big modules is very important. So if you have a large module that does some kind of computational task or requires a lot of additional data to be loaded, do it lazily. You can define a function that does an import inside of it, and Python will just do the right thing here. If the module's already been imported, it'll just be a no-op, and it's very fast. So it's fine to structure your code this way, and in a lot of cases, it'll make your loads faster. The other thing is that we preload almost the entirety of the Python standard library. So if it's a Python standard module, we've got it. It's loaded. It's good to use, more or less. There's a couple of limitations there. There's some kind of more rare character encodings that we don't load for a variety of reasons. But just kind of the takeaway here is think about module loading and the cost of loading modules. So then on the kind of data side of things, there's a lot of waste in large result sets. So if you do a query and you have a huge number of results and you're doing a lot of in-memory sorting and filtering, that's bad. That's really bad. Make the data store work for you. We provide a very rich set of queries and properties that lets you do very efficient queries, and figure out a way to make that work for you. Structure your data in a way that makes that efficient to query. Just try to use every single entity you get back from a query. So if you get back 10 entities and you only use one, maybe you could restructure that query to require fewer results. Again, and this translates to any system, avoid repeated queries. So if you have a landing page, eBay.com's like their landing page, a lot of other ones, Amazon, everyone's hitting that site, everyone's seeing the same information most of the time. There's no reason to do the query over and over again. Up until now, we had this thing, I call it incoherent caching, because it's not coherent. I don't know if that's right. But we let you actually cache inside the Python environment any kind of data related to your modules, any global variables, anything like that. So you can have an incoherent cache. But as of today, we've actually pushed out a memcache API, which I'm really excited about, which gives you all the semantics of memcache, all the consistency of memcache as known, memcached, all that kind of stuff, right out of App Engine, right out of the box. And it's that easy. You see here is an example. This is me using memcache. I have a set of results for my main page. I check the cache. If it's not there, I do the query, and then I put it in the cache. That's going to save a huge amount of work, wasteful work that you're doing over and over and over. And that's really, at this point, we're 3 quota. That's a very good thing to do. Okay, so that's kind of the Python stuff. It's kind of general stuff. Moving on, so numbers everyone should know. So this is something that we have at Google. This is something that's pretty well known to Nooglers and Google engineers. There's this thing Jeff Dean wrote with some other people called numbers that everyone should know. And it has everything from how much does it cost for an if, like a branch prediction in assembly code, how much does that cost, all the way up to how long does a packet take to get halfway around the world. And understanding the scales and times for performance and optimization and latency is really important. And so these are numbers everyone should know. So here are some numbers everyone should know about the data store in App Engine. So writes are expensive. Writes are very expensive. Why are writes expensive? Well, they're expensive because the data store is transactional. So when you do a write, you're hitting disk. You're actually hitting disk. We have to have transactional semantics. We need some kind of ACID-compliant transactions. So we need to hit disk to make sure that we can ensure that the data is consistent in the case of failure. So if you're writing to disk, that means you're also doing disk seeks. And the rule of thumb here is that 10 milliseconds is how much a disk seek costs. So just total simple math, like back of the envelope, 1 second, how many disk seeks can we do in 1 second? Well, we can do 100 of them, 100 seeks per second maximum. So you can kind of think of that as being like a maximum write throughput for a single entity on disk, and that's not that much. It can be a lot more than that, though. Like I said, these are kind of back of the envelope calculations, and it really depends on the size and shape of your data. I say shape, that means entities with a lot of properties or a few properties, big properties, index properties. That's kind of the shape of your data, and it also makes a difference if you're doing the work in batches. So if you do a lot of gets and puts, a lot of entities at the same time in parallel, you can kind of amortize some of this cost. But yeah, writes are expensive. But the good news is that reads are really cheap. They're ridiculously cheap. They're absurdly cheap. So the reason they're so cheap is that they don't have to be transactional. We don't have to wait for disk to catch up. We just need to know that what we understand on disk is correct. So a consistent view is all a read has to guarantee you. So the first time we get a request for a read, we'll hit disk, and then it's cached in memory. This is Bigtable doing all this work. All subsequent reads will then come from memory, straight from Bigtable. So here's another one of kind of Jeff Dean's list. It's 250 microseconds for a megabyte from memory to copy a megabyte from main memory from one part to the other. So again, the simple math, that's like 4 gigabytes a second, give or take. So for a megabyte entity, that's 4,000 fetches per second. That's 40 times what the write throughput was, and that's for a large entity. So I hope that convinces you that you want to optimize for reads as much as possible. The other way to think of it is that what's going to constrain your data the most is how you do writes. What's going to constrain your application the most is how you do writes, not how you do reads. And so it's really important to think about it that way when you're structuring your data. So what are the tools that we provide for you? So you want to scale your application, you want to store data in our data store with App Engine. We provide tools for doing that. So the simplest one are entities. Hopefully, someone told me this is a 201 session, so hopefully you know what entities are. If you've never used App Engine, that's great. I'm happy you showed up. You can use it today with open signups and all that. So entities, they're our fundamental storage type. Essentially, they're kind of, people say bag of properties. It's close to that. It's more structured. It's a set of property name-value pairs. Most of the properties are indexed, which means we can do efficient queries over them. There are other properties like blobs and text properties that are not indexed. So we provide kind of larger storage there. But really, when you think about it, it's best to think of it as an object store, not a relational database. So in a relational database, you have tables, and they have columns that map kind of primary keys and entries to each other, and kind of each table can kind of represent a relationship and all this other stuff. With entities, you define them as kinds, and it's much more of an object-oriented model. And that's a good way to think about it when you're kind of designing your data model. You think of it as kind of more object-oriented. And that might not seem intuitive at first because you hear big tables. You're thinking, oh, it's just a relational table. But big table is not like a relational database. It's very different. So the kind of object model is very important. So then the other thing is you can have, so following the object model, you can have kind of one entity relate to another entity through these kind of reference properties. And the reference properties are done by key. So every entity in the data store has a key. That's a primary key. It's like a way of identifying its unique existence. And that's how we identify them, and that's how entities can refer to each other to create hierarchies and relationships. So what are keys? So keys are big table rows. In big table, like it's that huge table that everyone keeps talking about, essentially it's just a distributed hash table. The keys are the way you look into the hash table, and then the entity is what's actually stored in the hash table, hash map, whatever you want to call it. So that means doing a get by the key is really fast. It's just a hash table lookup. That's what big table's optimized for in a lot of ways. It's very fast. There's no scanning. We just find it and copy it. One of the other things is that with keys, we can do transactions. And so this is a very important point. The transactional model that we have in App Engine relies on keys and this idea of keys. And I'm going to get into more of that later and the limitations there. But in the end, you can't do queries in transactions. And that's kind of a limitation that's a surprise to a lot of people. But you can do gets and puts. So you can do a get by a key and put the entity into the data store. We can do that efficiently. We can do that with a lot of different entities at the same time. So the model that you see people employ a lot of the time is do a query, figure out what I want to modify, then transact on those entities, use get to retrieve them by their key, and then modify them, and then put them into the data store. And that's a different way of thinking about things. And the reason it's like that is for scaling reasons, and I'll kind of get into why that's scalable and how we make that work. But getting back to keys, you can only have one ID or key name. It's kind of a unique human-supplied identifier for an entity. You can only have one of those per entity because it's unique. You can't change it after the fact, and it can only be 500 bytes, which is a lot, but it can be limiting in some ways. So this is where it starts getting more complicated. So when talking about kind of App Engine and scaling your applications and talking about write throughput as being your limiting factor, when I say write throughput is your limiting factor, another way to say it is that kind of transactions are your limiting factor. When you're doing writes, you're usually doing a transaction. You want your data to stay consistent. And unlike a kind of relational database traditional model of locking tables and rows, we do that with something called entity groups. So an entity group is a closely related set of entities, and they're actually stored physically and logically close to each other in Bigtable. Often, like actually physically close to each other, perhaps on the same machine, depending on how it works. And by having them close to each other like that, we can actually provide kind of ACID-compliant transactions across them. But the limiting thing is that we can't do transactions across entity groups. We can only do them at a single entity group at a time. So you kind of get this problem where you have some information over here and you have some information over here, and you want to lock both tables and then kind of transfer the data in between. We don't have an easy way to do that right now. You have to kind of employ a distributed transaction algorithm to do that. But there's many, many problems that you can solve with entity groups as they are, and I'm going to show you some examples of those. But thinking more about entity groups, when you lock one entity in an entity group, you're locking all of them. And that means that when you write to an entity in an entity group, it's serialized. It's serialized with all the other writes to that entity group. So if you have 10 entities all in the same entity group, writing to one of them, like if you write to the one over here and the one over there at the same time, those are actually in conflict with each other. They have to wait. One of them has to go first, and that's how we provide this consistent view. And that also means that it's also not a traditional lock. So that example I was just giving you, we have the writer over here for one entity, the writer over there for another entity. It's not like a kind of more traditional system where they lock the table and then actually operate. It's more like a competitive system where each side tries to complete its modifications before the other side, and whoever gets done first wins, and then the other side has to retry. And that's why some of the code looks the way it does, and you'll understand when you see an example. But the last point about kind of entity groups is that they're hierarchical. So if you find it useful to structure your data in a hierarchy, you can. This is child-parent relationships. You can have multiple levels of children. That's totally fine to do. You can do something called an ancestor query where you actually say, give me every child of this entity. And that's a really efficient query because of locality. The entity group, they're really close to each other, so you can do that query efficiently. And in the end, the hierarchy defines our transactional groupings. So if you have an entity and it doesn't have a parent, then that's a root node. And then any children of that root node will then transact as part of that same entity group. And so you can have as many of these kind of separate hierarchies from the root node as you want. And they can each transact kind of separately. So that's what this means. It's the data source scales wide. On one entity, we kind of have this limitation that we went over, which is disk seeks. We said 10 milliseconds. We said maybe a maximum of 100 seeks per second. So that's for one entity group, really. But there's no limit to the number of entity groups you can have. Bigtable mass is massive, and it scales very wide. Thousands of machines, thousands of disks, and you can have as many of these hierarchies of data working at the same time, transacting in parallel. And so this is kind of what it looks like. This is a very rough diagram, but you have root entities, they have children. Those are entity groups. We have transaction 1, 2, 3, 4. You can have as many of these as you want going on at the same time. This is how we scale. We scale wide. So pitfalls, large entity groups. When you have a large entity group, you have a lot of entities in it. That means that anyone who's trying to write there will have a lot of contention. Like if there are a lot of writes going into the same entity group, then everyone has to get in line to actually commit those changes. That high contention results in failed transactions. That's really bad. So pitfalls are not thinking about your write throughput. I keep stressing this fact. It's very important to do that. You want to structure your data in such a way that you optimize for your writes, for your usage patterns, for the kind of slow operations that need to be serialized. So there's good news. When you query, so you can't query in a transaction, but when you do query, you're guaranteed a consistent view across all entity groups. And what that means is that you don't see partial commits. You see only, for every entity group, you see the latest committed version. And that means that all the entities in that entity group will be committed at the same time. You won't see partial results. You won't see half of a transaction that's completed but hasn't gotten rolled back yet or anything like that. You're given the most consistent view available across all entity groups at the same time based on the most recently committed version, the last committed version. Okay. Everyone follow that? Any questions so far? Entity groups kind of hard to get your head around. Yes? Grandchildren. Yeah, you can have as many children as you want. I'm not going to stop you. Yeah. You can have the root node, you can have children of children, and so on and so forth. But if you have your grandchild down here and your parent or whatever, and then whatever, you have grandchildren and grandfather and your parent and your root node. When you lock a grandchild, you're locking all the way up. So everything in the hierarchy gets locked. And so people see this and they're like, oh, it's a file system, or I can do XPath queries on it. Well, maybe, but think of the kind of transactional impact of having a large hierarchy. There's some things you can optimize this way, but you need to think about the kind of transactional impact of that. So let's kind of go through some examples. One of the things we've seen a lot, so we pay a lot of attention to the Google group that I think hopefully a lot of you guys participate in. We have a lot of people on there. We're reading it all the time. It's really cool to see everyone kind of asking questions, participating, kind of banging their head against things here and there. We try to answer questions, alleviate your problems, all that kind of stuff. One of the biggest ones that we see over and over are counters. So people are, I want to have a count of this or that. I want to make my own hotornot.com. I want to have polls, whatever it is. And people hit this problem when they try to make a counter. So the first thing they try to do is they try to think of it like SQL or kind of traditional relational model, where they want to just use a count. which SQL is really good at. Well, Bigtable doesn't know about counts. That's the whole point. It has no idea. It knows how to find entities and scan through them, but it doesn't know how to actually count them. So that means that when you do a count, it's O of n, big O of n. That means if the count is n, it takes n operations to get there. It's not O of 1. It's not an instantaneous count. We have to actually scan through all the entity rows. So what people do then is they go, okay, well, I'll just have a property of an entity that's my count. And then every time a request comes in, I'll transact on this entity, and I'll add one, and then I'll put it back in the data store. The problem is that that's really a high update speed, and you get a lot of contention. You get a lot of people who are trying to write to that same entity at the same time. And so you get failed transactions. And this kind of highlights a kind of fundamental limitation in distributed systems. Global data is expensive. Global data is data that's shared between all of your users. Whereas local data, like your Gmail account, is something that can scale horizontally. Each person has their Gmail account, and those can reside on many different servers and scale wide. There's no global data that we're all kind of updating at the same time. And a global counter is global data. And this is a fundamental limitation of any distributed system. But sometimes you really need a counter. Like, let's say Slashdot needs to have a poll today, and they want to have a poll for how many people, what your favorite Linux distribution is or something like that. And that's global data, but it's kind of a necessary thing. So how would you implement that in App Engine? So the old model is kind of this one on the left. You have a single counter that you're updating transactionally. You can also do sharded counters. So sharding, partitioning, whatever word you want to use, is splitting a counter into multiple pieces. But what we're really doing here is that we're splitting a counter into multiple entity groups. And each of those entity groups can be transacted upon in parallel. And so what that gives us is it reduces our contention. So we say we have 10 shards. We pick a random shard. We transact upon that shard. We increase the count, and then we commit. And then when we want to figure out what's the total count, we do a transaction across all of them and then get the total. And so, in effect, this reduces the contention for writes by n, by the number of shards you have. And it's pretty easy to change the sharding factor because you just have to kind of add more entity groups. Now, there's obviously a kind of theoretical limitation to how many shards you could have, but I think from our back-of-the-envelope calculation, 100 operations or writes per second was kind of like the rule of thumb for one entity group. So if we had 10 of these, that'd be pretty good. So let's go into some code. Let's do an example. So here's a counter config. This is my counter. It has a name. It has a number of shards. And by default, let's say we have one shard. Then I have a counter, which is just the standard counter. It also has a name. And then the count defaults to 0. So this is very simple counter model. This is the same. The bottom thing is the same as the naive counter, the single no shard, like not sharded counter. So if I want to get the count, what do? I do a query. I query for all counters where the name is the same name, and then I just sum up the total. So that's pretty easy. Returns the count. But then when I want to actually increment the count, that's where it gets a little more complicated. That's where I have to do this kind of transactional thing. So I hope you guys can read this okay. Is that legible? Yeah? Yeah, maybe? All right, I'm going to walk through it. So see my mouse on there. So the first thing is so this is increment. Increment the name. This is the name of our counter. So we retrieve the configuration. The configuration says how many shards we have. So right here you see config.num shards. That's the number of shards. So we pick a random integer to figure out the shard number, the shard index. Then we create a shard name, which is the name, there's a typo there with the quotes, but yes, you take the name plus the index, and that gives you your shard name. Then we grab the counter entity. This is a get by the key name. We use the shard name and the index to do it. If the counter's not there, then we create a new counter. That's this if statement. It'll default to 0. Then we add one to the counter, and then we put it. So that defines our transaction function, and then we call at the bottom db run in transaction, and that'll actually run through this code. So if there's high contention at any time, the transaction will fail, and then we'll try again. So all the data will get rolled back, and then we'll try again. So I have this running right now, actually. So here's rollupcount.appspot. Feel free to check it out. Hellos is this one. I have a counter, so I can increment the number of hellos I've seen. Okay. And if I go into the data viewer here, you'll see I got a couple of, so I have a counter config, which has, there's my one from before, number of hellos. And you'll see the number of shards is 1. So now I want to modify this. Say I want 10 shards. Oh, that's great. Hey, what was that? All right. Yeah, hey, so cool. You'll notice the data stayed consistent because we were using a transaction there. It's very nice. So I think, okay, so this might be related to today's push. I apologize for it. But the code running here uses the same kind of scheme that's there. I was hoping to modify it while we're going here. I can try one more time. It's kind of fun. Let's see. Don't want 0. That'll explode. Yeah. Yeah, that's not going to go. Okay. All right. Well, I'll look into that later, guys. That's cool. All right. Anyway, moving on. So it scales. So yeah. All right. Well, let's gloss over that. So let's say that we try this again. We'll make this even faster than it was. So the simple answer there is to use memcache. We have memcache out today. It really lets you do a lot of things much more quickly than you could before. I don't know how many of you guys have used memcache before, but it's a consistent cache that's shared between all instances of your application. So when you make a modification in it, it shows up to all of your different kind of Python interpreter instances. So here we check the cache to see if the total's in there. If it is, then we're done. Otherwise, we recompute it and then put it in the cache. So that's great. It lets us kind of do, in the general case, when someone's just looking at the poll, when they load /dot, they'll just see the poll results and they're done. They just hit the cache. It's super fast. But what's really cool is we can also cache writes. So when a write comes in, we do this kind of fun dance to figure out the shard and update the shard. We do the transaction, and at the very end, we increment in memcache. So memcache actually has an atomic increment function. So you can have the counter in memcache. You can immediately update the counter in memcache as well as what's in the data store. And so that can gives you a kind of a fast path in the general case that's much, much faster than having to query the data store every time. But the thing about memcache is that it might disappear. Memcache, the cache kind of rolls off the end and goes away over time. And so you still need to do these data store operations to make sure that things stay coherent. But this allows you to kind of best of both worlds. Okay. Doing good on time. So hopefully some entity groups, you guys are understanding how you can do them you can transact on multiple entity groups at the same time in parallel. Another kind of example I want to go into is building a blog, which is kind of a different use case. So building a blog, when I say a blog, I kind of mean anything that fits in the general area of blogging. So content management systems kind of are similar. There's kind of a lot of things that fall under this general category of blog. And so I'm going to show you kind of a basic blog design, but really, there are many other things that could work this way. So let's just do kind of a standard blog. So we'll have multiple blog posts. Each blog has some comments. And the real difficulty here, and this is another one of those anti-patterns from the Google group, people are like, how do I page? I'm on page 1 of the blog. I want to get on page 2 of the blog. I'm on page 2. I want to get to page 3. And you can do offsets in your queries where you say, give me everything starting at entity result number 20. But if you remember, Bigtable doesn't know counts. It doesn't know how to do that. So you got to use your queries to actually efficiently determine where your data starts. So I'm going to show you guys how to use queries to do efficient paging. So here's how I think about this data. So I keep kind of ragging on everyone to think about your data, think about your write throughput. So with a blog entry, it's a low write throughput system. Blog entries go out, maybe once a minute tops. Usually it's 10, 20 a day. So it's a very kind of low throughput. That means we can have a global counter here, no problem. There's no problem in doing that because the contention would be low because the writes are low, the updates are low. And so what we'll do is we'll have a shared index. So the shared index is basically the blog index number. So this is blog post number 1, number 2, number 3, number 4. And what that gives us is a distinct ordering for our blog posts, so that we know that this is the first post and this is the kind of direction they need to go. And that lets us do efficient paging. So I'll show you how that works. So here are our models again. So we have a global index. That's our counter. It's just a counter. It looks just like the other one. And it has the current max index of your blog. So it starts off at 0. This is blog entry number 0. Then blog entry number 1, so on and so forth. And then we have entries, blog entries. They have an index, which is taken from that global counter. They have a title, and they have a body. So very standard stuff. You could add a when field. You could add tags to this with a list property. There's some fun stuff you could do very easily. The author, all that. So posting an entity. So posting a blog entry. So let's go through this. It looks a lot like the other one because it's very, very similar. This is the standard kind of transactional model of how you do transactions. So we post an entry. We take the blog name, the title of the post, and the body of the blog post. To start off, we grab our blog index, which is our counter, by the blog name. If it's not there, then we create it. So you see that idiom over and over again. Like if it's not there, then create it. Then we take the current maximum index from there, which starts off at 0. That'll be the new index for this new blog post. We increment that counter, and then we save the blog index. Then we create a new blog entry, and the blog entry has has a unique key name, which is the name of the blog and entry number 0. In this case, that's this right here. Key name is the blog name plus new index. So if new index was 0, then that would work. And the parent is blog index. And that's because this has to be the same transactional group. It has to be the same entity group. So it has to be part of that same entity group, and the easiest way to do that is to define it as the parent. So that's what we're doing here. And then add some other stuff. We put the index in, being the new index, the title, the body, and then we put the new entry, and then we do all of this in a transaction. So if at any point it fails in here, it'll try again, and whoever eventually wins will win, and all the data will stay consistent and rolled back if it has to, and committed, and all that kind of stuff. Okay. This is the hierarchy. So this is actually the parent-child relationship. We have a blog index, and we have the entries underneath it, and this is an entity group. So then, if you want to get an entity, we can just use get. We gave it a key name. It's a blog name plus its index. So my blog name's my blog. It's my blog 0, my blog 1, my blog 2. So getting an entity is just a simple operation. It's just get it by the key name. And this is super fast. This is the kind of distributed hash table thing that I was telling you guys about before. So optimizing for gets is a really, really useful thing to do. But if you want a page, then it gets more complicated. So I'm going to step you through this too. Okay, so getting entries. Let's say we have a start index. Let's say it's a number. If we want every entry, then someone will pass none. Let's just say that they'll do that. So default case comes in, start index is none. We want every entry. Then give me all the blog entries right here. That's this GQL query. Give me all the blog. Whoa, hello. Give me all the blog entries ordered by the index in descending order. So descending order, that means I want blog post 4, then 3, then 2, then 1. So I want the newest ones first, all the way back. So I fetch some number of them, posts per page. And I'll get into kind of more of that in just a sec. The other case is I give a start index to you. Let's say I give you a start index of 2. So show me everything starting after the second blog entry. Well, it's just I add a where clause where the index is less than the starting index, which will be 2. And that'll give me everything, including that one, going back. And that's an efficient query. That's perfectly efficient for Bigtable. So then you'll see the extra thing I did in here is I have this post per page plus 1. And that gives me an extra entity, more than I want to show per page. And the important thing there is that it lets me know that there is another page. That's all that is. It's just a little secret trick to get, I want 2 per page plus 1 more. And so if there's an extra one there, then we know that we have another page to show. And then we return back the number of entries I want to show on this blog page plus the extra one. And by returning back the extra one, then we can know, okay, well, the next page starts at index number 2, and then the page after that starts at index number 0 or whatever. So I also have a version of this running too. Hopefully this one works. So, okay, blog example.appspot. Please, nothing too vulgar. I'd appreciate it. Just wait like 5 minutes and you can do whatever you want. So here it is. So I have some posts. I can make a new one. Post in this, publish, boom. Okay, there's my fourth post. You'll see, if you look down at the URL, it's really small, but it says there's a URL there for a permalink, which kind of lets me view just go directly to this using a GET request. And then I can I can page through these very quickly, and you'll see that in the URL string it's kind of /start1 that says, okay, do this query starting at index number 1. And you can do the same thing for kind of paging backwards if you want to. Paging forward or backwards, either way, it's totally the same. You just have to kind of add another character to indicate the direction you're going. But this is an efficient query. We're saying, here's how I want to start, here's what I want to see. You can think of a lot of ways to expand on that, and that's how you do paging. It's really simple when you talk about it, but that's the right way to do it. One of the things, though, is what if you have comments? So comments are a high throughput kind of system. Someone posts a blog post, and then hundreds of comments come in really fast. So how do you deal with that? You can't have a shared index because that means that you have a high contention entity group. And that's where the scaling breaks down. That's where your apps stop being able to scale. So we need a way to allow for a high throughput of writes for comments, but still provide some kind of consistent ordering. So someone would be like, oh, well, let's just use the date. Let's use the date it's posted in milliseconds. Isn't that good enough? Well, yes and no. It's good enough in a lot of cases, but this is a distributed system, and we have thousands of machines at your disposal. The clocks are synchronized the best we can, but they're not always right. There's a large room for error with NTP and all that kind of stuff. So relying on synchronized clocks is a bad idea. But in some cases, it's good enough. So with comments, we want an ordering that's roughly this is the order the comments came in. But it's still very possible for two comments to come in at the exact same time. And so that's the example I have here. So on the left is kind of a timestamp. So this is May 26th at 10:11:04 and 0.1, 0.1234, and so on. So see, I have 4 different posts here that all start at 0.1234. So let's say I use that as my kind of paging parameter, where I did a query with this as the kind of my pivot point or whatever. So I do a query. I get back 3 entities, and let's say this one in yellow, that's the extra one. That tells me there's an extra page. So then I know, okay, well, here are my 3 entities before my post, and this is another post. Those are those 3 in bold. The next one is the extra one. So then when I want to show the next page, I'll just start with a post date equal to 10:11:04 and 0.123 seconds, 1.234 seconds. The problem is that matches this one. So if you tried to page that way, you'd end up getting repeated data. So that doesn't work. You can't do that. So there needs to be something else to solve this. And so what we're going for here is a way to break ties. So the way to do that is you can make your own composite string property. So Bigtable, to kind of take a step back, it uses lexical ordering for entity rows. So lexical means alphabetical, right? You have entity keys, they're in lexical order, and that's how we establish an ordering. And that's how you break ties, that's how you do paging, that's how you effectively query. And when you have a property and you're doing queries on that property, it's the same thing again. It's a lexical ordering of data. So if you can kind of transform your problem into a lexical ordering problem, then we can solve it. And it's very easy to do. So here I've made a composite string property. So I'm taking the post time, the user ID of the person who committed the comment, and then the ID of the comment. So what does that mean? Well, user ID is just the person. So in this case, like their username, their nickname from the user's API. And then I have a shared index. So that's what this thing on the right is, 0, 1, 13, 14. So although I can't have a shared index, a global counter between everyone here in this room for comments, I can have isolated counters all over the place. So if I'm logged in and you know who I am, then you can identify which counter I need to go to. And then I can have a high write throughput on that counter. And then any number of us can be doing that in parallel. So that lets us have all these different counters working at the same time, and then we can use that to break ties. So what that means is that I'll grab a counter in my entity group for bread. I'll increment it to the next spot, and I'll write a comment. That's all in my own entity group. Someone else is doing the same thing over here. But then when I query across all the entity groups, I get out this information. I get information from all the different entity groups, and you'll see that the ties are broken just fine. So here's the same query again where I started off at the beginning. The ones in bold are the ones I got back. The one in yellow is the extra one. And if you look there, the entity, the kind of composite property there, it has something that breaks ties. It has John 14. If I started doing another query at that exact same point again, I would start right there. There's a strict ordering. So, the way I'd like to compare this, I'd like to compare this to kind of the MapReduce thing. People say, MapReduce is this way of doing computation that's kind of a different way of thinking about problems. And if you can reduce your problem to a MapReduce problem, then you can solve it with MapReduce very efficiently. In the same sense, if you can convert your problem to something that scales like this, then you can scale really effectively. If you can convert your problem to deal with high write throughput with many entity groups, then you can scale really well. And so that's what you need to be thinking about when you're building a scalable application with App Engine. And so I have kind of an example of this kind of going somewhere. I don't remember which post had it. Somewhere in here. So I have comments. And these are just comments. And you can page on these. And the URL string looks a little funny. You could make it look nicer if you wanted. You see up there it has the timestamp, and then my name, and then number 2. But that's efficient paging. And again, so here's kind of the diagram of what's going on there. We have a user index with comments underneath it, repeated over and over, as wide as you want, all transacting at the same time. So, blazing through data here. What to remember? What are the big takeaways of this talk? So, number 1, you want to minimize your Python runtime overhead. You want to make it so that the cost that you're paying for serving a request is as low as possible. That means that when you warm up an interpreter the first time on a first request that comes in, you want to pay as little cost as possible. So use lean modules. Think about the cost you're paying up front. A lot of people will import everything they've got right at the top of their file. That's not necessarily the best idea. Minimizing waste. That's the other big thing. So try to use every data store entity that you retrieve. Everything you query for, try to use it. The other big one is think about gets and keys. Why do a query when you can do a get? Gets are super fast. They're just using big tables, a distributed hash table. If you can optimize for that case, which you can in a lot of cases, then do it. And that's also how that fits into our transactional model. If you want to do transactions, you need to think of things in terms of gets and puts and transactional operations as opposed to transactional queries. So then that goes back to the same point again. Structure your data to match your load. This is like what I've been saying over and over and over again, but optimize for low write contention. Try to have as many entity groups as you can, spread them as wide as possible, and break ties with kind of nice rules of thumb, like the user kind of comment counter that I showed you guys. And the last one is just memcache. Use it. It's really awesome. It'll speed everything up. You can throw anything in there. You can pickle an object. It'll toss it right in. There's a lot of things you can do that are wrong with it, but there's a lot of things you can do that are right. So give it a shot. It's set up and ready for you right now. If you download the SDK or if you deploy it to AppSpot, it's good to go. So that's the end of the talk. I'm here for Q&A, for any Q&A you guys want. Thanks a lot for showing up. I really appreciate you coming. Just come up to one of these mics if you got a question or anything like that.
Hey there. I'm interested in a memcache, and you showed an example of caching a get. How do you know when that's invalid? How do you know when to invalidate that cache when the number of rows have changed?
Okay, so the question is, when you're using memcache, how do you know that a get's no longer valid? Yeah. Is that the question? Yeah. So So when you say no longer valid, that means that it's expired, or it's referring to old data, right? So when you're writing for Memcache, you have to structure your queries in kind of the way you use the cache in such a way that you're kind of guaranteed that what's in the cache is always correct or it's good enough. So in a lot of cases with Memcache, it's okay to show data that's a minute old, 2 minutes old. That's sufficient. Because what you're trying to optimize is kind of read performance, getting data to users as fast as possible.
So basically use a timeout?
Exactly. You set an expiration. You say, I just did a count, and it was 22, and it's good for the next 60 seconds. And then everyone else who accesses the site for that next minute will see 22. And then finally a user comes in and will do the query again and then get out a new count. And so that's the trade-off. That is the trade-off. So,
thank you.
Yep.
Just a couple quick questions. Groups, I'm struggling to understand groups. They seem to be more logical rather than structural, because every time you go and create a new transaction, today it's these 3 objects in this group, but tomorrow it could be another 2. So do you keep creating these groups? They seem to be less structural and more logical.
Yeah, so that's right. They're a logical grouping. So they're a logical hierarchy of entities. The entities can be heterogeneous, so they don't have to be of the same kind. It's not like you define, here's the table of this entity type and the table of that entity type, and they're in the same entity group. You have hundreds, thousands of instances of these entity groups.
So you can have lots of overlaps then.
You can have overlaps. An entity can only belong to one entity group. That's the big restriction here. So,
but then would you get a cascading lock if you have an overlap?
So you can't have them overlap. But if you had a hierarchy with a lot of children underneath it, then yes, it's like a cascading lock, but it locks all the way to the root. So if you're down to the grandchildren and you have 100 entities in this group, the second you transact on one of them at the leaf, it's locked all the way to the root. And so that's kind of, the hierarchy is more for convenience.
Thanks. Second question is with regards to the App Engine environment. Is there anything special with App Engine that allows runtime scalability in addition to the Google production environment? So in other words, if you get obviously it's going to be a shared environment where you have lots of applications being deployed, and sometimes you can get a lot of traffic going through, and you need to scale out at runtime. Does App Engine have anything additional?
So I guess the question, to rephrase, is there anything that you as a user or an admin of an application on App Engine need to know about how your application scales under load, not just your load, but other applications in the same environment? No. You don't have to know about that. We scale for you, and we deal with that for you. And that's part of the design of kind of what we're supplying for you, and the kind of value of our system is that we provide isolation.
So it's guaranteed.
It's guaranteed. Well, that's a separate question that we should talk about offline. It's we're doing our best to give you the best quality service we can. Yeah.
All right. Thanks.
Yep. Oh, okay. Yeah.
What kind of tools are provided for indexing things such as text that can't necessarily be converted to a hash table key, such as you want your entity to represent information about a person or a product? Are there tools provided to scale queries that search textual information?
Right. So do you mean full text search?
Yeah, something like that.
Okay. Yeah. So we do allow for semantic types in the data store. There's a geopoint type. There are a couple other semantic types that we allow for, and you can query over efficiently. At this time, there is no full text search. We do have a searchable entity, which is in the X directory in the SDK, and it does some basic stemming and some basic kind of basic searching. So it will get you a lot of basic things, but it's not a Google search at this point. But yeah, that's definitely something we understand people have been asking for.
Okay, thank you.
Yep. Over here.
Yeah, I got a couple questions. One's a follow-up, I guess, on that one, which is really about is there a way to do like if you have one long field and you have 300,000 records and you want to figure out which fields or which records match a certain word in the field.
So the thing you can do the thing to look into is something called a list property, and a list property lets you throw a bunch of things into the list. Let's say 100 items, or some blurb like an abstract from a paper, or whatever, And then when you query over them, you can do an equals filter for a search term. And if that search term is in the list property, that entity will match. So that lets you do a very efficient query for entities in this way.
So each word is a member in the list? Is that
that's right, yeah.
Okay.
That's how searchable entity works.
Okay, and the second question is, if you have a sort of long-running background process that's like, let's say, pulling data from another site, how can you do that? I mean, it seems to be all request-based.
Yeah, that's something that a lot of people have asking about. They, what are our answers for offline processing? People have asking for cron jobs. We're well aware of the need for these things. People are asking a lot for them. We try to provide tools like the bulk uploader that lets you kind of drive these migration processes from the client side in a request-based model. But I think everyone's aware of the need for these kinds of tools. So
can you have like a super long-running request or something like that?
So those are some of the ideas that have been floated in the Google group about super long hanging requests that does all these things.
Now or something?
Yeah, at this point we're still focusing on request-based, but we understand that people need these things. So yeah.
Thanks.
Over here.
2 questions. First, are you posting the slides somewhere on the web?
Yeah, I think so. I think that I know the video is going on the web, so I'm pretty sure that all the slides are too. So
okay.
Yes. Okay. Yes.
And the second question is, for what is the general size of the, just the global variable cache and/or the mem cache?
So that's a good question. At this point, I can't talk about the actual size of the mem cache. I can just say it's best effort and very good. But I can say that also for the kind of incoherent cache, the size of your Python process, it's hundreds of megabytes, so it's large. So that's you have a lot of breathing room there.
Is it about the same as like just using global variables in the current App Engine?
You mean is memcache the same as using global variables?
Yeah.
In terms of size, I mean, because functionally it's totally different. Global variables in App Engine are not coherent between runtimes, right? So, but yeah, I'm not going to compare the two either, but I'm going to say that you should test out the memcache performance for yourself and tell us what you think.
Okay.
So,
thanks.
Yeah. Over here.
All right. Entity groups.
Yeah.
I'm trying to get my mind around.
Yeah, it's hard. I know it's hard.
Can you give me an example of how you would group many entities into one entity group?
How you would
why?
Oh, why?
Okay.
Yeah.
I come from a like you said, relational.
Sure.
Type
so
background.
okay. Yeah. So why would you put entities into an entity group? Is that the question? Yeah.
Yeah.
So you put entities into an entity group when they're closely related and you want to transact across all of them at the same time. So they represent a unit of transaction. Okay. And so in the same way that in a kind of a traditional model, like let's say you had a store website and you had a customer database and you had an inventory database, then you lock the customer's record, you lock the inventory record, and then you deduct some amount of money from their account and then pull some money out, pull some inventory, and then you commit the transaction across both. In that case, you need data consistency between all of these things.
Okay.
So entity groups solve that problem.
So when you're in one transaction, the entity group is only on that one entity, right?
That's actually not the case. It's that entity and anything else in the group can be part of that same transaction.
I guess what I'm saying is that instance of the entity.
Yes, yeah. So the entity would be the kind, like we call it an entity kind.
Right.
Yeah. So that instance of it, the kind of.
And then all that instances children, not necessarily.
Yeah, sure. Yeah.
For lack of a better word, it's not a whole table lock. It's a record lock.
Exactly. It's much more like a record lock because instead of transacting across a whole entity kind, you're transacting on one instance of that entity kind, one entity.
Okay.
And that entity represents kind of more of like a row level lock. And so that's the kind of granularity you're looking at.
Okay.
Yeah. Yeah.
Since they're a hierarchy, the ancestors can be deleted. Does that mean that I could continue having children and still have a manageable size entity group?
Yeah, so it's a logical relationship. If the parent identifies a key, and it's a lexical key, if the parent doesn't exist, it should still work because it's about how the key is lexically composed. And then if you rewrote the parent, you wouldn't have to update the children. It just works.
Okay, but the keys don't keep getting bigger and then get too big. Can you indefinitely keep it?
No, there's a limit. For the key name, it's 500 bytes, and then with the entities, with the parents, I think there's another limit that's a little bit above that. So there is a limitation for how deep you can go. Yeah,
okay.
Got it.
Can you hear me? Okay. I had a question about read consistency. So the query mechanisms that you were talking about, specifically in the context of paging, so as long as you use a key that you can lexically organize and that is unique enough, you will be able to do paging without repeating the same data that occurred in, say, previous page. My question is about how I can get repeatable reads in paging, meaning if I started at a particular point of time and paged through the contents of the data store, then I got one page of data out and I now want to get to the next page. How do I make sure that whatever was in the page, if I had run the query immediately after when I retrieved the first page, can actually be made available even if I might execute it a little later? In a sense, if one of the items in the second page was updated subsequently after I retrieved the first page, would I be able to see it ever in the second page?
Right, so another way to say this question is, how do you page like this when your data is no longer contiguous or records get removed in between?
Repeatable reads is my question, really.
Yeah.
Repeatable.
So that's a good question. And at that point, the kind of markers of your page would no longer be correct, right? So you'd have to move the markers or recompute the markers. And so that's why in this application, the kind of comments, those page markers are computed on the fly. And so if something like that happened where some of the comments got deleted, then the page URLs would change.
Right. So as a corollary, then the keys, if the keys are dependent on when you change the data, then it's not a good idea to. But I guess, all of the items that you showed in your examples were unmodifiable or immutable once they were created.
That's correct. And so there's some ways to work around that, to have mutable pages. You can do there's this way that it's kind of too complex to get into with this talk, but you can do checkpointing, where along the way as you're writing your data, you kind of figure out a checkpoint as a marker saying, oh, this is the end of page 1, this is the end of page 2. So there's some other things you can do, some extra entities you can write as a kind of a side table that lets you kind of put markers in place to prevent that kind of behavior, or to make it so that your page indexes are consistent regardless of what you do with your data. So that's a more complicated kind of example, but yes, that is the limitation of the example I showed.
So it's just a limitation of the example, but not a limitation of the app data store.
I don't believe so, and so I think it's a great question. So we should come up with an article to explain why that's not a limitation of the data store. But yeah, thanks.
Hi.
Yeah.
I'm from People Browser, and our issue is what is the best way to get data into Bigtable? We've built a product that is a cross-platform social network that takes personal data from MySpace, YouTube, Flickr, Twitter, JQ. We interface we've got peer-to-peer links with Java servers. We're getting high transactional data through our servers, and then we want to use Bigtable to serve the data to our users much more rapidly than we're able to serve it at the moment.
Right.
So our issue is how do we get it in there most efficiently? Do you have any thoughts about?
So right now we have a request-based model, and so we have tools like the bulk uploader to upload large amounts of data in a single request or a series of requests, but it's not as efficient as you would like. You pay this cost of the overhead, and I think we're well aware of that. We're working on, and I think Kevin Gibbs had a post about this in the blog. Tools for importing and exporting your data are something we take very seriously. We're working on. We want to address that problem. We realize that just as much as people want to get data in, they also want to get it back out. So we hope to have a good answer for that in the future.
And when you say future, next month?
I can't give you specific dates, but it's on the radar like everything else. Yeah. I think I have time for one more question.
I know that currently that the Python is the only runtime that you guys are supporting. Can you speak at all to what the roadmap is like for other potential languages that you're going to support?
Right. So I can't talk about the roadmap. I can say that we're working on it. We've gotten a lot of people. I know you're probably waiting for Fortran 77. We're trying our best. we got a lot of people who want that one too. So yeah, no, we're aware of this, and we're doing what we can, but we're not ready to kind of announce a roadmap or anything like that at this time.
Thank you.
All right, well, thanks a lot, everybody. I really appreciate it.